You know that sharp, kind of pungent smell when you open a bottle of vinegar? Well, you've just had a very direct encounter with a carboxylic acid. Turns out they're all around us. And in this explainer, we're going to break down exactly what makes them tick, from their physical properties all the way to the source of their acidic power. So, let's dive in. So, this right here, this is acetic acid. It's the star of the show in vinegar. And right at its heart is what we call the carboxyl group. That's the carbon double bonded to one oxygen and single bonded to another oxygen-hydrogen pair. Believe it or not, this one little group is responsible for basically everything we're about to talk about. Its polarity, its surprisingly high boiling point, and of course, its acidity. All right, here's our game plan. We'll start with the physical stuff, what they look and smell like. Then we'll dig into the chemistry of their acidity. After that, we'll get to the really cool part, how we can actually tune that acid strength. And finally, we'll wrap it all up with the key formulas and takeaways. Okay, let's start with the basics. What are these things actually like in the real world? We're talking about their physical states, what they smell like, and how well they play with water. So what's really fascinating here is that there's a super clear pattern. If you look at carboxylic acids with short carbon chains, say up to 9 carbons, they're these colorless liquids with some pretty unpleasant odors. But as that carbon chain gets longer and longer, they become these waxy solids. And because they're not flying up into the air as easily, they're pretty much odorless. It really is all about the size. So here's a little puzzle for you. For their size, carboxylic acids have shockingly high boiling points. I mean, way higher than other molecules that look kind of similar, like alcohols or aldehydes. So why? What's their secret? And this chart just nails the point home. If you take molecules that all have about the same mass, the carboxylic acids, that first bar there, just tower over everything else. There's clearly something extra going on here, some kind of super strong force between the molecules that takes a whole lot more energy to break apart. And here it is, the big reveal. It's a process called dimerization. As you can see in this diagram, 2 carboxylic acid molecules line up just perfectly to form 2 really powerful hydrogen bonds between them. They essentially pair up into a single, much heavier unit we call a dimer. This connection is so strong that the pairs can actually stay together even in the gas phase. So you're not just boiling one molecule anymore, you're trying to boil 2 that are stuck together. Now, thinking about solubility is kind of like picturing a molecular tug-of-war. You've got the carboxylic head, which is polar and absolutely loves making hydrogen bonds with water. We call that hydrophilic. But then you have the carbon chain tail, which is nonpolar and hates water. That's hydrophobic. For the smaller acids, up to about 4 carbons, the water-loving head wins, and they mix just fine. But as that greasy, water-fearing tail gets longer, it starts to take over, and the whole molecule just won't dissolve. Okay, so we've covered the physical side of things. Now let's get to the core of their identity, their acidity. I mean, it is right there in the name, after all. So this is the big question, right? We know what they look and feel like, but what is it on a molecular level that gives this entire family of compounds their defining acidic personality? It all boils down to this simple reaction. When you drop a carboxylic acid into water, it can give up that proton, the H+ ion, from its hydroxyl group to a water molecule. What you're left with is a hydronium ion, which is what makes the solution acidic, and this negatively charged molecule called a carboxylate anion. Okay, so how do we measure this acid strength? We use a scale called pKa. Now, it might seem a little bit backward at first, but just remember this one simple rule. A smaller pKa value means a stronger acid. As you can see on the scale here, the really strong acids have a pKa near 0, while much weaker ones, like ethanol, have a pKa way up around 16. Our friend acetic acid sits right around 4.76, kind of in that moderately weak range. So the pKa is simply the negative logarithm of another value, the acid dissociation constant, or Ka. Let's not get too bogged down in the math, though. Just think of pKa as a handy number chemists use to quickly compare how willing a molecule is to give away its proton. A small pKa means it's very, very willing. So why are they so willing to give up that proton in the first place? Well, the secret is all about the stability of what's left behind. After that proton is gone, the negative charge isn't just stuck on one oxygen atom. Instead, it gets spread out, or delocalized, across both oxygen atoms through a process called resonance. It's like spreading a really heavy weight across 2 pillars instead of just one. The whole structure is way more stable.
And this sharing of the negative burden is what makes the carboxylate ions so stable. This slide is a fantastic comparison. Look on the left. The carboxylate ion shares that negative charge between two identical, super electronegative oxygen atoms. That means they are great at handling a negative charge. It's a perfectly balanced, super stable situation. Now look at the right. A phenoxide ion is forced to push that charge onto the less electronegative carbon atoms in the ring, which are not nearly as good at stabilizing it. That's a much less stable situation, and it's precisely why carboxylic acids are so much stronger as acids than phenols are.
All right, now we get to the really cool part. Acid strength isn't just some fixed property. We can actually modify it. We can tune it just by changing the other groups that are attached to the molecule. So here's how it works. Imagine you attach a group that pulls electron density away from that carboxylate ion. We call this an electron withdrawing group, or an EWG. By pulling that negative charge, it helps spread it out even more, making the ion even more stable. And a more stable anion means the original acid was stronger. The opposite is also true. An electron donating group, or EDG, pushes electrons in, which intensifies the negative charge, destabilizes the anion, and makes the acid weaker. And of course, some groups pull way harder than others. This slide gives you a bit of a hierarchy. Groups like halogens, chlorine or fluorine, they're pretty good electron withdrawers. But a nitro group, that NO2, is even better. And then way at the top, a CF3 group has an unbelievably powerful pull. The stronger the electron withdrawing effect, the lower the pKa, and the stronger the acid becomes. And this is just a brilliant real-world example. Benzoic acid in the middle is our baseline, right? It's got a pKa of 4.19. Now, attach a powerful electron withdrawing nitro group, and boom, the pKa drops to 3.41. It's a stronger acid. But if we add a methoxy group, which is an electron donating group, the pKa goes up to 4.46, making it a weaker acid. You can literally see the tuning in action. Okay, we have covered a lot of ground. Let's just take a second to put it all together and summarize the most important ideas and formulas from our discussion. So here are the key mathematical relationships. Ka is the direct measurement of how much an acid breaks apart in water. But, like we said, we usually use pKa, its negative log, because the numbers are just easier to work with. And the most critical thing to walk away with is that inverse relationship. The smaller the pKa, the stronger the acid. Simple as that. So, to quickly recap our whole journey, the physical stuff like boiling point and odor, that's all about chain length and that special hydrogen bonding trick, dimerization. Their acidity comes from being able to give up a proton, which only works because the ion left behind is so stable. The absolute key to that stability is resonance. And finally, we saw that we can act like molecular engineers, tuning that acid strength up or down with different groups. And that brings us to the end. We've seen how these tiny changes to a molecule can have a huge impact on its properties. And that leaves us with a final thought. If we can control acidity so precisely, where else is this kind of molecular level control in drug design, in creating new materials, maybe even in electronics, fundamentally changing the world all around us?